Hey everybody! The purpose of this video is to get a little bit deeper into the idea of a p-value. The last question on your last exam. And I just want to make sure that you guys leave this leave this course with a really solid understanding of what a p-value is. I mean, I could spend, every day in class running through a different type of hypothesis test. But unless you really fully understand what a p-value is, the results aren't going to make any sense. So what I really wanted to get at here is understand what exactly that number means and how in particular it's formally defined. So the technical definition of a p-value, and we've expressed it a couple different ways in class, but the technical one, if you actually Google what is a p-value and you find a correct representation of it, more on that momentarily, it's going to say something along the lines of, it's the chance you get data at least as extreme as the data you got under a given null hypothesis. So you're going into a study assuming a certain null hypothesis, and then you are checking to see how well your data agrees with it. But it's not just your data, it's your data or more extreme. And that's really what I want this video to kind of hint at, is your data or more extreme data. So what I got running right here, as you might have seen, is the same exact a spreadsheet you guys had to run for the revised parameter test that you guys did on the epileptic seizures during the full moon. You'll notice the p-value that we're getting up here is exactly the same. Well, I shouldn't say exactly the same. It's probably close to the p-value that you got. I'm going to stop here. Whoops. I'm going to stop here for a second. And we're going to take a look at the results here. I'm keeping track, just like I did before, of the number of cases where 94 or fewer patients got seizures. And then the total number of trials would be the number of 470 item samples we're taking. And then here's just a simple ratio of what we're dividing. We're dividing this number into this number to get this number. But I want to focus on right now is, why am I doing 94 or few? I'm sorry, guys, I should really have my email turned off. I will do that right now. Why am I looking at 94 or fewer patients? Okay, so I want to address that question first. As you saw when you did the problem in your exam, this little yellow region down here is the 94 or fewer. But why is it 94 or fewer? Why not just 94? So to answer that question, what I wanted to do was I wanted to first take a look at what is actually being graphed. I'm going to slide this guy over a little bit. So when you do this parametrically, which is not non-parametrically, but the same argument will apply parametrically as non-parametrically. This is looking at it binomially. So if you have 470 elements in your sample and the probability of success is 0.25, this is all what we looked at in the problem earlier. These are the corresponding probabilities for each of the possible values of x. So from to 470, you could have no successes, 1 success, 2 successes, 3 successes, 4 successes, 5 successes, all the way up to and including 470 all the way at the bottom here. Now you might be wondering, wait a minute, Sean, why are there so many zeros there? Why are there so many zeros? Well, you have to think about why. Over the course of 470 trials, you shouldn't be getting 220 out of 470 successes if, in fact, the probability of success for whatever you're studying is only 25%. If you're getting more than half, then the probability should not be 25, it should be more like 50%. So you'll notice that the highest probability corresponds to the average. Whoops, we went right by it, which is that 0.4 or 4.25%, 117, which is essentially the average. N times P, 0.25 times, here, we'll just do the math for you. 0.25 equals 0.25 times 470, and you get 118 if we increase the decimal a little bit though. 117.5. So your average, halfway between 117 and 118, and here are your most likely probabilities. So that's why they spike there, and they also correspond on your graph up here between that 117 and that 118 right here, the highest point. Notice there doesn't seem to be anything over here or over here. Now you know there is something there. There is something there because they have to be. This 0 over here is not really 0. Let's increase the decimal on it. Oops, let's increase the decimal on it. I wonder how far out we have to go until we actually see something. It's gonna be pretty far. Let's keep going. Gonna make a liar out of me. There it is. So it's not 0, it just rounds to 0. It just rounds to 0. So the idea is all of these numbers actually do have, they actually do have values. It's just that they don't start showing up in the 4th decimal place until you start getting quote unquote close to the average. There we go, 85, which is still far enough away to be suspect, but at least it's close to the 4th decimal place. So why do I bring this up? Well, I bring this up because when you look at this graph, to identify a p-value on this graph, I mean, the most common probability was at 118, right? 117, 118. But look how likely those probabilities are. 4.25%. That's not very likely, is it? That's not very likely at all. 4.23%. Both of those by themselves are under 5%. So even if you were to run a hypothesis test and come back with a sample that came with 117 successes out of 470 trials, your probability value of just that is 4.25%. Well, that falls in under our 5%, doesn't it? And that makes it seem like, oh yeah, that makes it seem like we're too low. Well, that doesn't make any sense. You landed exactly at average. So how can this be so low? Well, think about it a different way. You know that in this curve, the entire curve needs to be 100%. The area of the entire curve is 100%. That means each of these little tiny areas have to add up to 100%. Well, there's a lot of them. There are 471 of them altogether. So 471 that have to add up to 100%, you can do the math on that. On average, they have to be 0.047. But then again, on average, that doesn't make any sense because they have to be weighted for the entire distribution. Excuse me, not 0.047, 1 over 470. But that's assuming a uniform distribution. This is hardly uniform. It's more likely towards the middle. But regardless, even though that's the case, there's still 471 individual elements that have to be added together to make the number 1. Stands to reason these values can't be very big, okay? Especially in a bell-shaped distribution like this. It gets even more extreme when you get to the normal distribution. Now, a normal distribution, you're going to notice it's shaped very similarly to the binomial distribution. And we learned this many, many, many weeks ago as to why they should be very, very, very similarly shaped. But the normal has even more values for the random variable. It doesn't just go discretely 0, 1, 2, 3, 4. And these, the ones I've got listed here, aren't even all of them. This is just by tenths, 28.2, 28.3, 28.4. So you might realize that by the time you finally get down to ones that actually get, if you will, close to what the average is, you start seeing them creep up. But look how many are microscopically small. You have to get very, very close indeed before you actually start seeing, there they are, measurably significant results. And these still are extraordinarily small. 99, it should be closer to 117. As you start getting closer, again, you begin to notice that these guys, oh, we're getting close. And they're starting to creep up just like they did for the binomial. There, right there is your true average, the true largest value. But again, because they're broken up even more, you have to look at the individual components of these curves. They basically are going to be subdivided down and divided and conquered, if you will. So in other words, the reason you need to not just look at your data and one point is essentially because on these curves, let's go back to the original curve, on these curves, your data only makes up one tiny little smidgen. Even if your data is near the high point, its overall percentage of the entire 100% is going to be pretty small, even if it's the most significant chunk. Make sense? Hopefully it does. Now, as far as why you would shade to the left or to the right or into both tails, well, you have to think about that from a logical point of view of a hypothesis test. Suppose you were trying to show, as you were in this case, that people got fewer seizures during a full moon cycle. Well, 94 was our cutoff, and you might stop to say to yourself, well, 94 is pretty low. It should have been 117, 118. We got 94. That's down quite a bit. Well, would 95 then surprise you more or less? Would 96 surprise you more or less? Would 100 surprise you more or less? Those numbers wouldn't surprise you more because they're getting closer to the average value of 117. What would surprise you more would be the values that are more extremely low than 94, 93, 92, 91, 90, 50, down here, 50, 25, 20, 15. So the ones, if you have a hypothesis that the seizure rate is too low, which your data points to, your data says, oh, look, 94 is under 117 and a half. What's the chance of 94 being the worst case scenario, but the worst case scenario is being the closest to 117, but it even being lower? And that's why you shade off. You want to move away from the null average because those are the ones that are showing significant differences from the null average. So you kind of got two things you have to think about in this problem. The first one is that your data itself represents, even at modal representation, a very small percentage of the overall curve. So looking at just the data by itself is going to give you an unreasonably small number. And then you have to look at your data and further away from the null. So in a left-tailed test like this one, you'd go and this way. In a right-tailed test, you'd go and this way. In a two-tailed test, you'd slap 2 down and go both ways. But nonetheless, you always have to shade away from your assumed center. Well, I take that back, don't I? I take that back. I retract that statement. If you've got a correctly phrased hypothesis, you always shade away from your assumed center. The whole point of this problem was originally they were trying to shade the wrong way. They were saying we got more seizures, so they actually shaded this way and shaded to the right, which crossed the center. So assuming let's edit that statement. Assuming your hypothesis is set up correctly, you're going to shade away from that because you're trying to see what's the chance of your data or even more extremely different. Okay, and I hope that got you enough information to knock this last 10 points of the question out. Feel free to email if it didn't, and we'll catch you in class.